Good evening, ladies and gentlemen. My name is Aimee Mibaraka, and I am joined with Lindsay Collins, and this is the final conclusion of the project that we've been doing in Engineering 460. Just to start off, just as in any research paper, we just looked around different articles just to give us an idea of our project at hand, and some of those articles that we looked was the peculiarity of robotics in mining and demining robotics, which is a potential catalyzer for technological innovation in Chile. And these two articles was just to open our minds and our eyes to see how robots work and how it can be used to implement them in mining. And the articles that we used for our model was the Robotic for Mining, and this was written by Vladimir Kunyak. And what he was talking about, we kind of like we took his model that he wrote in his paper and we implemented in our research. And of course, this, as you can see, the picture here is the model that he proposed, where the robots are going to be in the mines for excavating and discovering the natural resources, and a more detailed model of what he was talking. It's of course in our paper, but if I can just give a summary of how robots are just going to be in the mines, and via communication they were kind of like going to excavating and discovering the natural resource that is in the mine. So of course they will literally take on the job that the miners or human miners would be doing. And another model that he proposed was this second image here, where he said of how they're gonna the robots are gonna use the routing in order to optimizing the more efficient way to get to the resource. And this was very important, since we're all industrial and system engineering. It's all about making a process efficient, but also optimizing the time it takes for a robot to get to a natural resources. So these were the two models that we used from Vladimir Kunan selected article that he wrote, and I'm going to pass it to Lindsay. He's going to talk about the rules.
So now we're going to dive into our model, since we kind of already gave an introduction for what we're doing and some of the research based behind our models. So the most important part of the model itself is the rules. And there's 6 main rules that we've used that help determine how the agents make decisions and what goes on kind of behind the scenes. So the first rule, and debatably the most important, is the natural resource selection rule. And this is basically how the robots decide if they're going to go and excavate diamond, gold, coal, or copper. And so we've created an algorithm to help decide which they should go to. So after they have deposited the resources they already have, they have to go through a cycle and determine a p-value, which is the profit available for selecting a resource for each of the 4 resources. And the formula is shown. So basically what they calculate for each one of the resources is they take the value for that particular resource, and so they're all ranked in priority. Obviously diamond is the most important, followed by gold, then coal and copper. They subtract the processing time that it's going to take to get that particular resource times the amount of robots that are already there, because a queue is going to form, so they're going to have to wait longer. Also, they have to factor in the distance. As you can see, the distance formula is shown there. So that's a very important rule for our model. Another important rule is the base return rule. We've set it up so there's 4 different bases, and what happens is the robots can only deposit so much at a certain base. So after one base is full, that adds another set of systems engineering and another set of algorithms where they have to decide from there where they're going to go. And they can use the rules above to decide which base is closest and how they should determine their path from there on out. There's the obstacle avoidance rules, which is obviously just talking about how they avoid things such as pitfalls and mine collapses. There's the communication and work allocation rules, which is how the robots signal each other and how they can determine it's kind of like a GPS, they can determine their proximity in the mine compared to where other robots are. They can also determine things such as the amount of natural resources remaining at any location, the status of the base capacity, and things like that. There's also routing and tunneling rules. Since they do tunnel randomly, they also have to decide their destination, where they're going to go, and then which base they're going to return to after they have their resources. So this is all important in determining our simulation. And then our final rules is obviously extremely important, our minimization rules and our optimization rules. So they obviously have the shortest path that they want to follow. They also want to get this done in the least amount of time because they're only set for 2,000 steps, so they can only go for a certain amount. Also, it's important to find the most valuable resources. Obviously, like I talked about earlier, we've set up this optimization formula to determine profit, and they're going to get more for a unit of diamond, so it's more important to find that, but they also have to factor in the other options of how long they'll be waiting and how far they are from the diamonds. So there's also the architecture behind our simulation. First is kind of the behind the scenes where we have the simulation architecture, and this is made up of 3 parts. First we have the agents, which are, in this case, just the robots. We also have the fields, which is the different dimensions. So we have the bases, the obstacles, the resources. Also the objects, which is kind of the algorithms and other things that determine what decisions are made. We also have the execution architecture, which is kind of the display. So we have 5 different portrayals that are used. We have the base sensor portrayal, the resource sensor portrayal, sites portrayal, obstacles portrayal, and also the agent. So these are basically layers of our display that are stacked on top of each other to show what's happening, and we'll get into that later when I go ahead and show the simulation. So I'm then going to wrap up what else we've talked about in our paper.
Okay. For our ongoing research, just as any other research, we had to ask ourselves some different questions. And if I can just point out the main ones that we can talk in this video was, the first one was, of course, the multi-agent simulation, which is the software that we use to simulate our model and see how it was going. And the first question that we had to ask ourselves for this was if we had chosen if there was any other simulation that we could have used in our model. And for our simulation, for the foundation that we had used, or the idea behind, was also ant foraging, which is kind of like where ants are going to find food and they communicate with one another to where the food is. So that question in research, we had to ask if the foundation that we use, we could have used another foundation that was a better, closer to our model. And another big one we had to ask ourselves was the profit maximization. The profit maximization, of course, goes with the routing and also how much money it's actually the robot mining is bringing to the business. So those might be the main question. And if I can also point out, the one was the queuing. With this, since there's different natural resources the robots were getting, we had to ask ourselves if a queuing problem were going to be present in. If there were problems such as queuing in the mines, how can the robots communicate and where to go where there's a shortage of robots? So those were some of the main problems or questions that we had to ask in our research. And of course, those broad challenges, just as any other research, we brought a challenge of the complexity of the real mining versus the simulation world. It also kind of like brought challenges of knowing the programming and kind of like working with the simulation devices. So these were the main parts of our paper, and I'm going to hand it to Lindsay, who's going to talk about the simulation and conclude the video.
So we're going to wrap up by giving an overview of the simulation, and we're not going to go deep into the code because this is discussed in further detail in the previous video for project part 9. But we do want to run it and kind of just talk through it, compare it to our conference paper, so you get a good look at what we're trying to accomplish through this. So if we go ahead and play our model, you can see obviously the 4 bases in each of the 4 corners where the 20 robots start, and 5 robots start at each base. And you can see as they tunnel through looking for the different resources, the different factors that we talked about earlier that are setting in. For instance, there's always the reward factor, like we talked about. They're going to go for the different resources that have more priority and things like that. We also have to keep in mind the queues and how long it's going to take to get back to different bases And we also have to remember that the bases get full, so they have to determine which base to go to and how this all plays in. There's also the optimization techniques that we talked about, since obviously our whole goal of this entire robots mining optimization is to maximize profit. We have to factor in that the robots are mining to get the most amount of precious materials or valuable materials in the least amount of time, because this is automatically going to stop after 2,000 steps. So the robots are being programmed to find the most amount of food, so they have to factor in, like we've talked about many times, the distance they are, the amount of time they're going to have to wait to get the specific resources, and also how full the bases they're returning to while still avoiding the obstacles. So in conclusion, we think that this model has some good implications for real-life situations, and we also believe that robots in mining overall creates a more efficient process and can solve a lot of safety, and it can really optimize the process that goes along with the mining industry. And we look forward to continuing to work on this simulation and perfecting it, and seeing what improvements could be made. So I thank you for watching.